3,000 years ago, engineers living in some of the hottest regions on Earth solved a problem that today still costs homeowners billions every single year. And they solved it without electricity, without compressors, and without any of the machinery that modern air conditioning depends on. They buried pipes underground and allowed the Earth itself to regulate temperature. And the uncomfortable truth is that this ancient system still works today, often outperforming modern cooling systems in efficiency, lifespan, and cost, yet it remains almost completely absent from mainstream construction. By the end of this video, you will understand exactly how it works, why it quietly disappeared, and how it can still be built today. To understand this system, you have to go back to ancient Persia, where temperatures regularly exceeded 40 degrees Celsius, in a landscape where survival depended on controlling heat rather than escaping it. Persian engineers developed a system known as the Qanat, an underground network of channels carved through rock and soil. It was originally designed to transport water across vast desert distances, but it also created something unexpected. As hot desert air entered vertical shafts and moved through these underground channels, it passed through Earth that maintained a stable, significantly lower temperature than the surface. By the time the air reached the buildings above, it had cooled naturally, without any mechanical intervention. When paired with tall, wind-catching towers, known as badgers, these systems created a continuous flow of cooled air through homes, effectively functioning as a natural air conditioning system in one of the harshest climates on Earth. And this was not an isolated discovery. Across different civilizations, separated by geography and centuries, the same principle emerged again and again. In Egypt, subterranean ventilation shafts were used to reduce heat inside structures. In the Roman Empire, long underground corridors known as cryptoporticus served both as passageways and passive cooling systems. In the city of Yazd in modern-day Iran, wind towers still stand today, continuing to direct air underground before releasing it into buildings at lower temperatures. Different cultures, different tools, but the same underlying realization. The Earth, just a few meters below the surface, maintains a nearly constant temperature throughout the year. At a depth of roughly 2 meters, the soil remains between 10 and 13 degrees Celsius, regardless of whether the surface above is experiencing extreme summer heat or winter frost. This makes the ground itself a thermal buffer, a natural system capable of absorbing heat when air is too warm, and releasing heat when air is too cold. The modern version of this ancient principle is known as the Earth tube, or sometimes the Earth-air heat exchanger. The concept is simple. Air is drawn from outside and forced through a long pipe buried underground. As that air travels through the pipe, the surrounding soil absorbs excess heat. On a hot summer day, when outside air might be 35 degrees Celsius, the temperature can drop by 10 to 15 degrees before it enters the home. In winter, the process reverses. Cold air passing through the same system is warmed by the stable ground temperature. It is one system providing both heating and cooling, without the need for traditional HVAC infrastructure. Unlike modern systems, which degrade over time, this approach relies almost entirely on materials that do not wear out. A buried pipe, properly installed, can last between 50 and 100 years. Compare that to conventional air conditioning systems, which typically last between 15 and 25 years before requiring replacement. But this is not theoretical. Modern buildings have already demonstrated how effective this system can be. The Earth Ranger Center in Canada uses multiple buried earth tubes to regulate incoming air, reducing energy consumption significantly. Studies have shown energy savings of over 50% when earth-air systems are integrated into building design. In Europe, where proper standards have been developed, these systems have been in use for decades, particularly in Germany, Austria, and Denmark. And yet, in much of the United States and other regions, they remain almost completely unknown. They are not banned outright, but they are effectively excluded. Because the real reason these systems are rare has very little to do with performance and everything to do with economics. The global HVAC industry is worth over $170 billion. That industry depends on equipment that requires maintenance, repair, and eventual replacement. Compressors fail. Refrigerants need to be replaced. Filters need to be changed. Service contracts generate recurring revenue year after year. Now compare that to an earth tube system. One installation, one buried pipe, no compressor, no refrigerant, no recurring maintenance, a single low-energy fan, if any, consuming minimal electricity. From a business perspective, it is not a product. It is the absence of a product, and that is where the conflict begins, because industries built on recurring revenue models do not benefit from solutions that eliminate the need for ongoing spending. But economics is only part of the story. The other barrier is regulatory. Most building codes simply do not include provisions for earth tube systems. There are no standardized guidelines, no universally accepted installation protocols. When inspectors encounter something not explicitly covered in the code, the default response is often rejection, not because the system is unsafe, but because it does not fit within the framework they are trained to evaluate. One of the primary concerns raised is radon. Radon is a naturally occurring radioactive gas that can accumulate in enclosed spaces, and it is linked to lung cancer. This concern is legitimate. However, in regions where earth tube systems are more common, proper design standards have already addressed these risks. Sealed piping systems, proper drainage, and filtration can effectively mitigate these issues. In other words, the problem is not the system itself, but how it is implemented. And where proper standards exist, the system works. Which brings us to the most important question. If this system is both effective and proven, how do you actually build one? The process begins with understanding your site. Soil type plays a critical role. Moist, dense soils like clay conduct heat more effectively than dry, sandy soil. Depth is equally important. The pipe must be buried at least 6 feet underground to reach stable temperatures. Shallower installations reduce effectiveness significantly. The pipe itself must be smooth-walled, typically PVC or high-density polyethylene, with a diameter of at least 6 inches. Corrugated pipes are avoided because they trap moisture and promote mold growth. The length of the pipe determines how much heat exchange occurs. A typical system uses between 100 and 200 feet of buried pipe. As air travels through this length, it gradually approaches the temperature of the surrounding soil. The pipe must be installed with a slight slope, typically around 2%, to allow condensation to drain toward a collection point. Standing water inside the pipe is one of the most common causes of system failure. At the intake, the pipe rises above ground level and is fitted with a screen cap to prevent debris and pests from entering. Inside the home, the system connects to a ventilation unit, often combined with a heat recovery ventilator. A small inline fan can be used to maintain airflow, though the energy consumption is minimal compared to traditional systems. For regions with higher radon risk, an alternative design uses a closed-loop system, where a fluid circulates through underground pipes and transfers heat through a heat exchanger inside the home. This approach eliminates direct air exchange while preserving most of the thermal benefits. And once installed, the system requires almost no maintenance, no refrigerants, no compressors, no complex mechanical parts, just the steady, predictable physics of the Earth itself. Which raises one final question. If a system this simple, this durable, and this efficient has existed for thousands of years, why did we replace it with something far more complex and far more expensive? The answer is not that the old system stopped working. The answer is that we stopped building it. Because over time, knowledge was replaced by products, simplicity was replaced by systems, and independence was replaced by dependence. But the ground beneath your feet has not changed. Its temperature is the same today as it was thousands of years ago. The physics still work. The only difference is whether you choose to use it.